All right, let me ask you a quick question here. It says resistances in parallel must have the same current through them, potential difference across them, energy dissipated in the form of heat, all of the above and none of the above. Take 50 seconds to talk to a person next to you and your time starts. Oops, sorry. All right, the correct answer is potential difference across them, because if you remember, if you have two capacitors, the potential difference across them should be the same. It looks like most of you got this thing right. The energy that is dissipated in the form of heat doesn't have to be the same. So suppose, you know, these are the 2 points and here is one resistor and here is another resistor. Let's call it R1 and R2. What we will find is that V sub R1, which is the potential difference across this point and this point, or this point and this point, is the same as the potential difference V sub R2. Right? Is everybody agreeing that V sub R1 will be equal to V sub R2? That's what we mean by saying that the potential differences are the same. On the other hand, the power dissipated don't have to be the same, because if you remember, power dissipated is V square divided by R. So even though the V's are the same, you can see that the power dissipated in this resistor is going to be P1 is going to be V square over R1 and P2 is going to be V square over R2. And so P1 doesn't have to be equal to P2 unless the two resistances are exactly the same. Is that making sense? The voltages or potential differences are the same for the two. All right, let's look at another question. It says a 2 ohm resistor and a 4 ohm resistor are connected in parallel to a 6 volt battery. The power dissipated by the 2 ohm resistor is how much? Take 1 minute to answer this question. Talk to a person next to you. Thank you so much. Thanks a lot. All right, you can see in this particular case, basically the situation is this, right? These two capacitors, sorry, these two resistors are in parallel, and here you have some battery which is providing a 6 volt, you know, which has a potential difference of 6 volt. So in this case, you are given, for example, that one of the resistors R1 is, let's say, 2 ohm and R2 is 4 ohm. So in this case, what would be the power dissipated across 2 ohm in 2 ohm? Can I use this? Yeah, I could. And from here you can immediately see that P1 will be equal to V square divided by R1, which is equal to 6 volt square divided by 2 ohm, which is 36 divided by 2, which is 18, and the unit of power is energy per unit time, should be the unit of energy divided by time, so that is joules per second, or in short, watts. Right, so that's the correct answer. The correct answer here is D. Looks like most people got it right. All right, you know, let me ask you, it looks like the other questions we haven't done yet, so I'm not going to ask you as a concept test right now, but let me just ask you a question without asking it as a concept, because I don't have it there. Suppose if you had a circuit like this. Suppose you were given a circuit which looks like this, 2 ohm, and this was, how much was this, the second one? 4 ohm. And let's say you have another one here which might be, say, 1 ohm, and now you have a 6 volt battery. Okay, I want everybody to talk to a person next to them. This is not a thing over there. I want you to tell me how much is the potential V of R1. Is V of R1 still going to be equal to V of R2 here? Yes, but that's not going to be equal to 6 volt. You know why? Because the battery no longer is in parallel to these two. You can see that one end of the battery now is not directly connected to this junction, right? Do you see that there is a resistor here? So in this case, the battery is not in parallel with this resistance and this resistance, even though, is everybody seeing that these two are in parallel with each other? So like, look at this junction and this junction, they meet. This junction and this junction, they meet here at this, you know, sorry, this wire and this wire, they meet at this junction. So if you like, you know, if I call this thing VR2, the potential difference, say, between this point and this point, I can still say that V of R1 is equal to V of R2, right? I want you to tell me two things. I want to know, what is this? The second thing I want you to tell me is a question very similar to this: how much is the power dissipated in this 2 ohm resistance? And that would be easy to find once you know this, right? Because then you can again say it's whatever is this V square divided by R1. Is everybody seeing that? But this thing is no longer 6 volt, because some of the battery voltage is dropping across this 1 ohm resistance. Do you see that? So everybody should take 1 minute, talk to a person next to them, and I want to know what is V of R1 or V of R2, which are the same anyway in this situation. Is this clear? Please talk to a person next to you. All right, somebody help me figure out how I, start how to do it. Just give me some clues on how I should start doing this problem. Go ahead, please.
You want to eventually find the equivalent resistance.
Okay, one way to do it would be to find an equivalent resistance. That would be one way to do it. We could do it that way. What is the another way? I mean, we could directly also use Kirchhoff's rule, right? I mean, we could just say, okay, let's use it in this loop, maybe, right? Could we do that? So equivalent resistance would be a fine way to do it, because once you found the equivalent resistance of these three, what can you do after that? So do you see that these two are in parallel? You can find the equivalent of that, using the equivalent of that and adding that to this, because the equivalent of these two will be in series with this one. Then you can find the total resistance, and if you found the total resistance, V divided by the total resistance will give you the current coming out of the battery, and then you can say, oh, that current gets split up into two parts here. You can figure out how much is the current going through this. You know, if we call this current, let's say I1, we call this current I2, and we call this current I. There is I flowing in this branch from here to here, and that splits up into I1 here and I2 here. This is I2. you can figure out what I1 and I2 are, and once you found I1 and I2, what can we how can we find V of R1, the potential difference across this resistor? Will it be I1 times this resistance? Yeah, from Ohm's law I know that across any resistor V will be equal to I times R, right? So I know that potential difference here should be I1 times R1, across this it should be I2 times R2, and I know since these two are in parallel, I1 times R1 better be equal to I2 times R2, because V of R1 is V of R2, right? So, but the other way to do it is just to maybe use, let's say, Kirchhoff's rules here, A, B, C, D. If we use Kirchhoff's rules, then, you know, we can again talk about, oh, what is the, if the current I is flowing through this branch, this, you know, here and here, it should, the potential differences should add up to 0 here, right? Similarly, you can do it, potential differences should add up to 0 here. You can again figure out how much should be I1, etc., and you can be done. So both of them are fine ways. Do you want to do it using equivalent resistance? Let's do it that way. So when we do R equivalent, do you see both ways you can get the same thing? You have to realize that I, you know, which is the current coming out of the battery, should be equal to I1 plus I2. That's something that we do have to realize. Suppose let's find R equivalent. We know that first equivalent of these two, I hope everybody sees, I'm going to just do it in one line, will be 1 over 2 plus 1 over 4 ohm, right? And to that, this is basically what we can call R12, and if we are calling this R3, this is in series with the equivalent of these two, so I'll just add to it this 1 ohm resistance. And so this is then going to be equal to 1 over, half is like 2/4, so this is 3 over 4, so that's 4 over 3 plus 1. So which is equal to 7 over 3 ohm. Right? Is everybody with me? This is the equivalent resistance of the circuit, so I can find I easily. Then I will turn out to be V of the battery divided by R equivalent, and so that will be equal to 6 volt divided by 7 over 3 ohms, which is 18 over 7 amperes. Right? Now that I found I, does everybody see that I will get split up into I1 and I2? Right? Also, is everybody agreeing that if V of R1 is equal to V of R2, what we are saying is I1 times R1, let's give it a name, R1, and this is what we are calling R2, this resistance is R2, then is everybody agreeing that I1 times R1, which is the potential difference here, V of R1 should be equal to V of R2? So since V of R1 is equal to V of R2, what we have from there that is I1 times R1 is equal to I2 times R2, right? From Ohm's law, V is equal to IR across a resistor. Okay, in addition to this, we also know that I is equal to I1 plus I2, and this I we already know is this, 18 over 7. So 18 over 7 amps is I1 plus I2. Do you think we can use, you know, so looking at this thing, is everybody seeing that I can write I2 is equal to I1 R1 over R2? All I'm doing is dividing by R2 here and I get I2. Why do I want to get that? Because then I can put I2 here, because I have to solve for I1. If I need to figure out what is V of R1, that can be written as I1 times R1, isn't it? Is everybody seeing what we are trying to do? So we need to figure out what is I1, and so we need to eliminate I2, and I can eliminate I2 by saying, oh, this is I1 plus, instead of I2, I can write it in terms of I1. By the way, R1 and R2 are given to us. R1 is given to us to be 2 ohms, and R2 is given to us to be 4 ohms. So this is basically half of I1. So you can see that instead of I2, I can write half of I1. And so half plus I1 plus half I1 is 3 halves I1. So what I get from here, since there's no place, let me write it here. What we get is 18 over 7 is equal to 3 halves I1. That means I1 is equal to 18 times 2 divided by 7 times 3, which is 3 and 18 get cancelled and you have 6 left. So that's 12 over 7 amps. Now that you know that the current here is that, is it easy now to find V sub R1 or V sub R2? What will be V sub R1? Anybody wants to tell me? Folks, go ahead. Huh? Anybody wants to tell me what will be V sub R1? Is it going to be I1 times R1? Wouldn't it? Yeah. So we already know that's 12 over 7 amps multiplied by R1, which is 2 ohms. And so this is 24 over 7 volts. Should that also be equal to I2 times R2? Yes, since these two are in parallel, we know this is also, if you were asked, this should also be equal to V sub R2. But the thing is, so how much is the power dissipated here? You know, power dissipated in R1 will be V sub R1 square divided by R1, right? And so that would be 24 over 7 square divided by 2, this many watts. What would be another way to find the power dissipated, folks? If somebody did this, I1 square R1, because power can also be written as I square times R. Will that give you exactly the same thing as this? Yes, it better. In fact, you should check at home whether this number turns out to be the same or not, because it better turn out to be the same. If you do 12 over 7 amp square times 2, these two should be the same. Those are two equivalent ways of getting the same thing, right? Any questions about this, folks? So I want to point out that if there is a resistance here, you cannot assume that the battery is in parallel with these resistors. You can see that here the problem was more complicated than the previous problem that I asked you, because in this case the battery itself was in parallel with each of these resistors, right? So do you see that this was a lot easier than this case? The difference here is that there is another resistor here, and that makes the battery no longer be in parallel with each of these individual ones, even though these two are in parallel with each other still. So I1 times R1 is still equal to I2 times R2. That means V sub R1 is still V sub R2, but it's not equal to battery voltage because of this. Any questions, folks? Remember, I did an experiment last time, you know, and I was discussing this. We have this R is equal to rho L over A, and I showed you that if you double the area of cross section by connecting two wires, you know, next to each other, we actually doubled the area, the resistance went down, and that increased the current if the voltage is kept fixed. Isn't that, you know, V is equal to IR. If, you know, if R goes down, V is constant, so because suppose I'm keeping the V constant, then this would mean that I should increase. Do you remember? Okay, the other thing that I was trying to show is that if you double the length, the resistance should go up. And you know, I think there was some loose connection, and that's why I was not able to show you, because somehow the ammeter kept reading 0. But the point was there was some loose connection. So I'm not going to show the demo again, because this is a different demo that I want to show today. But basically the idea is that if the length increases to 2L, you can see that R, you know, goes to 2R. In this case, if you keep V constant, the current should go down, right? Do you see current should go down? how much? Current should go to I over 2 actually. You can see because V is equal to IR. So if R goes to 2 times R, I should go to I over 2 if V is constant. Okay. Any questions about that? Okay, I also wanted to tell you about a few things that are from previous chapters that I just want you to know. One thing is this unit called electron volt. Do you know what is it? What is that a unit of? Yeah, electron volt is actually a unit of energy, but it's not SI unit. What is the unit that you always use in SI unit? Joules. So the question is, what is 1 electron volt? So here is a non-SI unit of energy called electron volts, or in short you can write it as EV. What is it? It's, remember, so 1 electron volt is the work done when you move an electron through a potential difference of 1 volt. So suppose you have 1 volt here. Suppose this was a positive plate and this was a negative plate of a capacitor. Let's say V was 1 volt. Okay. If you move an electron, suppose you take an electron and you move it from this plate to this plate. The work done in moving this electron through 1 volt potential difference is called 1 electron volt. Does that make sense? Okay, so 1 electron volt then is the work done in moving the electron over a potential difference of 1 volt. Remember, work done was the change in potential energy, right? Negative of change in potential energy, and negative of the change in potential energy can be written as the charge times negative of change in potential, right? So 1 electron volt can be written as, the charge of the electron times change in the potential. I mean, I'm not worrying about because this is the work done. When this delta V happens to be 1 volt. Right? What is the Q for the electron? Do you remember Q for the electron was 1.6 times 10 power minus 19 coulomb? Right? Do you remember that? And that if you multiply by 1 volt, that would be 1.6 times 10 power minus 19. What's the unit coulomb times volt called? It better be the unit of energy. Does everybody see that? I'm not saying anything fancy. All I'm saying is that change in potential energy has a magnitude equal to work done, and change in potential energy can be written as Q times change in potential. So this is equal to the work done, and I'm saying change in potential when this is 1 volt and when this charge is that of the electron, we call that 1 electron volt, right? So I'm just saying when Q is equal to E and delta V is equal to 1 volt, the work done is called 1 electron volt. Okay, and so I'm trying to show you what is 1 electron. So coulomb times volt is how much? This is Q, charge of 1 electron. This is 1 volt, potential difference. This should be this times this, which is coulomb times volt is joules. So what you've learned is that 1 electron volt, what we learned is that 1 electron volt is nothing but 1.6 times 10 power minus 19 joules. This is how to go from non-SI unit to SI unit. This unit is going to be very useful, for example, in your chemistry classes, because in chemistry classes when you're dealing with, say, for example, hydrogen atom and trying to figure out what are those discrete energy levels and things, those energy levels, you can see 1 electron volt is a very small energy, right? At least in terms of joules. If you're used to talking about energies in joules, 1 electron volt is 10 to the power minus 19 joules. So when you're talking about the energy of electron in a hydrogen atom, it turns out its energy in the lowest energy state might be minus 13.6 electron volts. Okay? So people don't want to keep writing minus 1.6 times 10 power minus 19, 1.6 times 10 power minus 19. It's kind of that, it's not a very convenient unit. So people use instead of that electron volt. So even though it's a non-SI unit, it's a very popular unit to use in chemistry courses when you're dealing with those energy levels of atoms and molecules and things like that. So that's a good thing to know. This came up somewhere in the previous chapters, but I just wanted to clarify this. Okay, the other thing that I wanted to tell you about was what is conductivity? I think you should know the meaning of this word conductivity. Do you know what is conductivity of a material? How might it be related to this thing called resistivity? Just can you make a guess? Go ahead.
Is it 1 over?
Yeah, it turns out that conductivity of a material is defined as 1 over its resistivity. You know, so for example, a metal has a very low resistivity, so its conductivity will be high. So we can define something called just a few terms that I want you to be clear about. So sigma is 1 over rho, and this is called conductivity of the material. By the way, I want you to see that this is not the best name, sigma, for conductivity, because have we used sigma for something else also? Remember, we have used it for charge density, charge per unit area. So from context, you will have to tell when we are talking about conductivity and when we are talking about charge per unit area, because they have the same symbol. It's like, you know, speed has symbol V, voltage has symbol V, volume has symbol V. You have to be careful when you're talking about what. But this is nothing but 1 over resistivity of the material. Okay? So materials that have low resistivity will have high conductivity. Any questions about this? Okay, then we are done with all of the tidbits that I wanted to cover. Let's now talk about what is an ammeter and what is a voltmeter. I'm sure that you're already familiar with what those terms mean. So can somebody just tell us what is the meaning of those things? And then I'll tell you a little bit about how to connect them in a circuit and whether they have large resistance, small resistance, and why. Any thoughts on what is an ammeter? Go ahead. Yeah, ammeter is a device that is used to measure current. Okay, what about a voltmeter? Go ahead. Yeah, it's a device that can be used to measure potential difference at any point in the electrical circuit. So if I wanted to measure the potential difference between A and B, I'm going to connect what is called a voltmeter in the circuit. Okay, now let me say a few things about ammeter and voltmeter. So we are saying ammeter is a device to measure current. Okay, this device is always connected in series where we want to measure current. Where current is to be measured. Also, ammeter should have a very small internal resistance. So what do I mean by this? I'll explain in a second. So for example, in this particular circuit here, if I wanted to know what is the current here, you know, in this part here, what I'm going to do is I'm going to connect a device called ammeter, and it's usually written like this, and there are 2 wires that go out of it. These are the 2 wires that you'll connect in the circuit. So what I'll do, if you tell me, oh, find the current here, I'm going to connect an ammeter connect the two leads with the wires like this. Do you see it's connected in series in this part? If I want to find the current here, should I be connecting it here like this? If I want to find the current here, should I be connecting an ammeter here? Okay, if I want to find the current in this branch, I'll connect an ammeter here, an ammeter here, maybe an ammeter here. Can anybody tell me whether these three ammeters will read the same thing or different things? They should read the same thing, because do you see this is one branch of the circuit, there's no break, there's no junction. So that if there's no junction, according to junction rule, whatever is current in should be current out, current in should be current out. So from all the way from here to here, the current is the same. This ammeter, this ammeter, this ammeter should read the same thing. What about this one? This one should read a different current, right? Because this should read I1. These three ammeters are reading I. What about this? These two, should they be reading the same thing? Yes, and they are reading I2. If I put another ammeter here, that will also be reading I2. Now the other thing that I say is that ammeters should have very small internal resistance. You know, if this device itself has a resistance, if suppose that device itself has a resistance, then in my mind I have to say, oh, this is an ammeter and it itself has an R. Do you see that that R will change the current in this branch? And I don't want to change the current in this branch, so I would rather not have an ammeter that itself has a large internal resistance. So I want its internal resistance, any resistance of the ammeter, to be roughly 0. Because if that is not the case, then the ammeter itself will change the current in different branches, and we don't want that to happen. Is everybody clear? So ammeter is always connected in series to wherever we want to measure the current, and it has a small internal resistance. Now voltmeter, it turns out voltmeter should always be connected in parallel in a circuit between those two branches where you want to find the potential difference, like he said, and a voltmeter should have extremely high internal resistance, as high as possible, you know, infinite compared to any other resistances in that circuit. So voltmeter has the opposite thing. So it's used to measure voltage. That is potential difference. This is connected in parallel. Between 2 points where potential difference is to be measured. And this should have a very high internal resistance. And here I'm writing R of the voltmeter should go to infinity compared to anything else, all the other resistances in the circuit. Why is that? So for example, you know, in this circuit, suppose if I wanted to measure, let me remove the ammeters just so that the picture is a little cleaner. Suppose I wanted to measure the potential difference across this resistor between these 2 points, right? The thing is, so what am I trying to measure? Am I trying to measure I2 times R2? If I want to measure the potential difference, you know, on that side and this side, between those 2 points, I'm trying to measure I2 times R2. That means I'm trying to measure V sub R2. What I'm going to do is I'm going to connect a voltmeter here, which is written like this with a V. So voltmeter is often denoted with a symbol V, and it has leads like this. And do you see that this is now in parallel to this? Now here is the thing, I'm saying to you that the internal resistance of this voltmeter should be very high. So this voltmeter should actually have internal resistance R internal, that should be very high. Why is that? If I am trying to measure the potential difference between these 2 points, let's call it like, you know, C and D, do I want this current I2? When I connected this voltmeter in parallel, do you see that the voltmeter is in parallel to this resistance that I'm trying to measure the voltage across? It is, right? Okay, what do I want? Do I want all the current I2 to go this way? Across this? I do, because if I'm trying to measure I2 times R2, I don't want any current to deviate and go through the voltmeter, because otherwise it's going to change the current through this, and I won't measure I2 times R2, I will measure something that is less than I2 times R2. So I do want all of the current to flow through the resistor so that you know, so in other words, I want the current through the voltmeter to be roughly 0. Does everybody appreciate why I want the current to be 0? Because I do not want to suck any current I2 that was initially going through this resistor, because I want to measure the true current I2 times R2. That's what I'm trying to measure, right? Now how can I avoid this? If these two are in parallel, is everybody seeing that, you know, I2 times R2, let's say this is IV, what we have is this. If those two are in parallel, let me write here. Do you see that I2 times R2 should be equal to I sub V times R internal of the voltmeter? Isn't that true for things in parallel? Is everybody appreciating that this V here, you know, should still be the same as the V here? That's what I'm trying to measure, and that means I2 times R2 should be IV times RV or R internal. I'm just calling it R internal, right? But hey, the good thing is that I don't want to change this I2, and if R internal is very large, look, I2 times R2 divided by IV is equal to R internal, and you can see from here, if IV goes to infinity, sorry, it's the other way around, this is R internal, this is IV, you can see that if R internal is very large, IV is very small, right? So that the product of the two, something very large times something very small, still is the same as I2 times R2, but the good thing is, since IV is almost 0, it's not changing the current that we are trying to measure, because what we are trying to measure is the true current. Any questions about this voltmeter? Anybody? So the conclusion is voltmeters are always connected in parallel, and they should have very high internal resistance compared to any of these other resistances in your circuit, right? So if these things are just a couple of volts, a couple of ohms, this thing maybe you know, thousands of ohms, then that would be almost, you know, or if you can make it 1,000,000 ohm, that's even better. That's an even better ohm meter, right? So as R goes to infinity, it gets more and more precise in reading what you're trying to read. Any questions, folks? All right, then let me now talk about a battery that is not ideal, a battery that has internal resistance. Because remember we said earlier that, you know, when you take a fresh battery, it might actually have a potential difference of 3 volts across it, but as you use the batteries, the electrodes get corroded, and then the battery provides a smaller and smaller potential difference, I mean has a smaller and smaller potential difference across it, right? So the thing is, basically we ought to be able to represent the fact that the battery is not ideal with something called internal resistance of the battery. So what we are going to do in our circuit is when we represent a battery that is not ideal and which has an internal resistance, we are typically going to have a little r, which is the internal resistance of the battery, and this is what we mean by the inside of a battery. So maybe, for example, we could have a circuit like this where this could be R1, which is 1 ohm, this is R2, which is 5 ohms, and there is a R, maybe this starts out being very small, maybe 0.01 ohms, but then over time, as the battery's electrodes are corroding, could this increase? Yeah, maybe it will become 0.1 ohm after some time, 0.2 after some time, 0.5. It could keep increasing. After some time, the battery won't be very useful. So I'm just saying, think of this whole thing over here as being part of your battery. And this thing is the internal resistance of the battery, which is always going to be shown as a resistance in series with the battery. Okay? Now the question that I have for you is, in this case, what would be the power output of a battery? So what is the power output of a battery which has internal resistance? What is the power output of ideal battery? Do you remember, for an ideal battery, the power output was just I times V. The current that comes out here, let's say that there's a current I coming out of the battery. If you multiply that with the voltage, let's say this is a 3-volt battery. So the current times the voltage will be the power output for an ideal battery. But I'm claiming that if the battery has internal resistance, then the power output is not I times V, it's going to be different. What is for a non-ideal battery, which has an internal resistance, power output will be not just I times V, but I times V minus I square times R. Because do you remember, power dissipated in a resistor is I square R? So now what's happening is that some of the power is getting dissipated in the form of heat inside the battery itself because it has an internal resistance. Do you see what I'm saying? So less power goes elsewhere. So you can see that over time, as R is increasing, will the power output of a non-ideal battery keep decreasing? As the little r, the internal resistance increases, and there will be a time where this R becomes so large that this thing is almost 0. And at that point you throw the battery out, you say it's useless, it's not giving any, the power output of this battery has become so small it's negligible, I'm not going to use it for my purposes. So that's how you modify the power output for a non-ideal battery. You subtract off I square times the internal resistance's resistance. Any questions about this, folks? Okay, then the last topic from this chapter is RC circuits. So we have talked about 2 kinds of circuits so far. In the previous chapters, we talked about circuits that only had capacitors. In this chapter so far, we have talked about only circuits that had resistors. Of course, batteries are always there. Now we are going to talk about circuits that have both capacitors and resistors. And these circuits are called RC circuits. Now, here is the thing. If you have an RC circuit, you obviously can use that circuit, first of all, to charge the capacitor or to discharge the capacitor. So we are going to talk about 2 different kinds of processes. One in which we are going to charge the capacitor. In one case, we are going to discharge the capacitor. Let's try to talk about 2 different kinds of RC circuits. And after dealing with RC circuits, you'll see that later on we are going to talk about this new thing called inductor. An inductor is nothing but just coils. And it turns out inductors are an important component of electrical circuits also. When you look at any electrical circuit chips, you'll see resistors, capacitors, and inductors. And so later on we'll start talking about what about the circuits which have all these three elements, because those are the circuits that are most prevalent in any electronic circuit. But let's talk about RC circuit, and the first case let's talk about is charging a capacitor. So we'll start out with a very simple circuit, a circuit that has a resistor, a circuit that has a capacitor, and a battery, obviously. And let's say initially the switch is open. Let's say this is a, battery which is, who knows, let's say this is a 3-volt battery. Let's say that the resistor is 2 ohms. Let's say the capacitance is resistor has a resistance of 2 ohms and capacitance is, let's say, 2 farads. So when the circuit is open, and let's say initially we start with this capacitor which is uncharged, there are no charges on the plates. One of the things that we have always done in this course and that you have done in your exploration assignment is you have actually rubbed something and that electrophorus device, and you have actually produced charges, and then you've touched it to one of the plates. That's not how you would do it in a real thing, right? In a real circuit where things have to be done over and over again, you would want some kind of a circuit to automatically do the charging and discharging. So here is a circuit that will automatically do it. Now tell me, what do you think will happen? So right now it's uncharged, this capacitor is uncharged. As soon as I close this switch, what do you think will happen? Electrons from the negative will start going towards like this, right? Wouldn't the electrons start moving like this in the circuit? Okay, if the electrons start moving like this in the circuit, will we say that there is a current flowing this way? Because we, have chosen this strange convention that we say that a current is flowing opposite to the direction of flow of electrons. Right? Current is the charge of the electron that flows per second through any cross section of the wire. Now, so if the electrons are coming here, do you see that they are going to accumulate here? Right? Where are they coming from? They are leaving behind a positive on the other side. So every time an electron comes here, there's a positive that's left behind. So, and by the way, this is an insulator, right? Between the two plates of a capacitor, you always have an insulator. That's how a capacitor is defined. It has two conducting plates separated by an insulator. So these charges can't jump. So basically the charge has a path to move from here to here, and then it accumulates. Again, it accumulates, etc. By the way, as more and more charges are accumulating, is the potential difference across this capacitor increasing? Yes. And there will be a time when this potential difference will become the maximum that the battery provides. In this case, the current will stop. Right? Wouldn't the current stop? So what do you think happens to the current as a function of time? Does the current start out being maximum initially when there were no charges on these plates, and then slowly decreases, and then goes to 0 when the capacitor becomes fully charged for this battery? Yes. And in fact, what you will see is that the current actually exponentially decreases. And what you will see, right now we are going to derive it, you will see that charges on these plates will accumulate exponentially. So the amount of charge that is collecting there will exponentially increase. The current that is flowing in this circuit will exponentially decrease. Let's try to derive it, okay? What we are going to do here, is we are going to use Kirchhoff's rule, for example. That would be a good thing to do. So for Kirchhoff's rule, let's choose, for example, A, B, C, D. And what Kirchhoff's voltage rule will tell us that VAB plus VBC plus VCD plus VDA should be equal to 0. Who wants to tell me what is the change in potential when I go from A to B? Look, I'm going in the direction of current, right? Yeah, very good. It's negative I times R. If you go over a resistor in the direction of current, the potential drops, right? So VAB is minus I times R. Everybody comfortable with that? It's negative? Okay, what about from, look here, from B to C. From B to C, you are going over the positive. B is connected to the positive terminal of a capacitor and C is connected to the negative terminal. If you go from B to C, what should happen? Should that be a drop in potential? Yeah, so this should be minus V sub C, where V sub C is the voltage across the capacitor. Okay, what about from C to D? We have said we'll ignore the resistance of the copper wire, so 0, nothing happens there. From D to E, do you see I'm going from negative to positive of a battery? So that's going to be a plus E. Is everybody with me? Now what is V sub C? Do you remember from the relation between the charge, capacitance, and the voltage across the capacitor? What should it be? Remember this? Q was equal to C times V sub C, right? And that means V sub C should be equal to Q divided by C. Shouldn't it? Also, I want to be able to figure out how much is the current in the circuit and how much is the charge in the circuit. I want to write the current in terms of charge. How can I write the current in terms of charge? Remember, current was what? dq over dt, wasn't it? So I can write this as dq over dt times R. Instead of V sub C, I can write Q over C plus E is equal to 0. What is the only thing we don't know in that equation? Yeah, we know how much is the resistance, we know how much is the capacitance, we know how much is the battery voltage. The only thing we don't know is how much is the charge on the capacitor plate as a function of time. You know, after a time t, after I close the switch, how much is the charge on the capacitor plate? That's the only thing I don't know. The only problem with that equation, so Q is the only thing I don't know, the only problem is that that's a differential equation. But I'm hoping that most of you have actually done differential equations. Even if you haven't, I'm going to just write down the answer for this differential equation. This is as easy as it will ever get. The differential equations that you will deal with in a differential equation course are going to be a lot more complicated. This is the first thing that you see in that course. You know, this is a linear first order differential equation, ordinary differential equation. It's that simple. Okay, so this is the simplest one, and the answer to this is, so solve this differential equation to find what Q will be, and the answer that you get is this: Q is equal to C times E 1 minus e to the power minus t divided by R times C. This is what you find. So this is the solution of this equation. Okay, you know, more than knowing how to solve a differential equation, because I'm not going to ask you in the exam to solve a differential equation, I want you to understand what this solution really means. Okay, so I want everybody to take 1 minute to try to plot. But before I ask you to plot it, I want to also find the current. Can we find the current now? Now that we know Q, can we find the current? Anybody wants to tell me how to find the current? Do what with this equation? Take its derivative with respect to time, because I know current is dq over dt. If I take its derivative with respect to time, I will get the current. So let's try to find it. So the current will be dq over dt. So the current is d over dt of this thing, C times the EMF of the battery times 1 minus e to the power minus t over R times C. Does everybody know how to take derivative of an exponential? What is it? So tell me, who wants to tell me what is this thing? if I have d over dt of e to the power a times t, this is equal to what? A times e to the power at. Do you remember this from calculus class? Derivative of an exponential is an exponential. If you have some constants, you just pull it out. Right? So what do we have here? Here actually we have two terms here. The first term will give us what? D over dt of a constant. We have c times e times 1. The derivative of a constant is 0. So the first term is 0. And then you have the second term. The second term is minus c times e times d over dt of this thing, e to the power minus t over rc. Right? What is it? Minus c times e. Should I pull the constants out? Yeah, let me pull the constants out. Do you see in this case a is what? A is minus 1 over rc. Right? This a here is minus 1 over rc. That's the constant. So if I take this minus and combine it with this minus, minus and minus gives me a plus. Divide by rc. And then I have e to the power minus t divided by rc. Sorry. So you can see here then that the current turns out to be E divided by R e to the power minus t divided by RC. This is what the current is. Now I want you to do 1 minute of talking with anybody who's sitting next to you and try to plot for me what would be the charge as a function of time from this equation and what would be the current as a function of time from that equation. So I want you to plot Q as a function of time and I want you to plot for me current as a function of time. Everybody 1 minute, because you should be thinking about it yourself. And the good thing is, think about the limiting cases. Think about what happens at t equal to 0 when I just close the switch. The capacitor was uncharged then. What happens very long time after that when t goes to infinity? Alright, anybody has any thoughts on what will this plot look like? Go ahead, anybody wants to volunteer? What would that look like? See, this is the, go ahead please.
Charge will increase exponentially.
So initially what was the charge?
Initially?
Yeah, initially the capacitor was completely uncharged, right? So initially there were no charges, right? When I just close the switch, that is time t equal to 0. And you can see from here, if I put t equal to 0 here, what is e to the power minus 0? Yeah, basically e to the power 0 or e to the power minus 0 is 1, right? So as he correctly pointed out that the charge will exponentially increase, but exponentially increase from 0 charge. So initially, does everybody see that at t equal to 0, this thing says at t equal to 0, Q is equal to C E 1 minus 1, because at t equal to 0, e to the power minus 0 is 1. So this is basically 0. And that's exactly what we would have expected, but because as soon as I close the switch, that's time t equal to 0, there's no charge on the plates, right? You can see the charge is exponentially increasing, but let's think about what happens at t equal to infinity. So what is t equal to infinity? T equal to infinity means very, very long time after I close the switch, right? So what happens after very long time after I close the switch? Does anybody know what is e to the power minus infinity? Because this is minus infinity, right? Notice that numbers won't matter. These are some finite numbers. So long as you have infinity, that dominates here. So basically what we have here is e to the power minus infinity, which can be written as e to the power 1 over e to the power infinity. What is this? Yeah, e to the power infinity is infinity, right? So 1 over that will be 0. So this is 0. So basically what we are saying is t going to infinity, q will be equal to c e 1 minus 0. Is everybody appreciating this will be 0 because of this? Okay, so then this is just equal to c times e then. So then he is absolutely correct. What happens at t equal to 0? There is no current. At t equal to infinity, there is current equal to, sorry, at t equal to 0, there is no charge. At t equal to infinity, the charge becomes c times e, and at that time, that's the maximum amount of charge that you have, right? The current has stopped. So the plot would look like this. This plot would look like at t equal to 0, it starts out at 0, increase exponentially, and it plateaus out at some value which is q max equal to c times e. What is E? E is the EMF of the battery. By the way, what does that tell you about the potential difference across the capacitor? What has happened to the potential difference across the capacitor for the maximum charge? Remember, the potential difference is Q divided by C. Remember this? Q is equal to C times the voltage across the capacitor. So that means Q over C is Vc, right? And so can you tell me what would be a plot of Vc as a function of time? What would this plot be? Anybody wants to tell me? Will its shape be exactly like this? Wouldn't it? Yeah, it's just Q as a function of time divided by some constant, which is C. C is a constant for a given capacitor. So the shape would exactly look like this, except that that plot, what will be the maximum? You know, Q divided by C, so E will be the maximum. The EMF of the battery, the voltage of the battery will be the maximum voltage in this case. So this should be exactly like this. And this maximum value here, V max, will be the EMF of the battery. This is what we were saying earlier, right? Weren't we saying that if you close the switch, charges will start accumulating, charges will start accumulating, charges will start accumulating. When this voltage here becomes equal to the battery voltage, current will stop. You have the maximum amount of charge accumulated for that battery, and the voltage has become the battery voltage. Any questions about this? Okay, then what about the current, the plot for current? Anybody wants to tell me looking at this? Go ahead, please.
The maximum current at t equals 0 will just be 1 over r.
Excellent. So what he's pointing out is that at t equal to 0, here is my t equal to 0, the current will be maximum, I max, and he has correctly pointed out that I max will be E divided by R, and then it will exponentially decrease, and infinite time after the switch is closed, it will go to 0. Why? Because look at this thing here. Do you see when I put t equal to 0 here, e to the power minus 0 is 1. So the current is E over R at t equal to 0. That's what I'm plotting here. Okay, what happened at t equal to infinity? This becomes e to the power minus infinity. E to the power minus infinity is 1 over e to the power infinity, which is 0. So long time after, the current has gone to 0. And it goes to 0 exponentially. Is everybody comfortable? So now I could ask you another question. I could ask you, can you tell me what would be a plot of the voltage across the resistor as a function of time. Suppose in the exam this is the question you were asked, because I often ask questions like this actually. I often ask, give plots, and I ask, what would have, which of these is the correct plot for which case, for example. And if you physically can think of the situation for charging and discharging, it should be a breeze. So who wants to tell me what should be a plot of V sub r as a function of time? So what is V sub r? V sub r, looking at this picture, V sub r from Ohm's law is just I times R, isn't it? V over a resistor is I times R, always, from Ohm's law. V is equal to IR, okay? Because we are considering ohmic resistances. So this thing is I times R. Shouldn't the plot of this look very much like the plot for current? Because all we have done is we have multiplied the current with some constant value R. So it should be exactly like this, right? So this plot should look like this also. What should be the maximum value, folks? Vmax should be the EMF of the battery. It should be, right? Because you can see Imax is E over R, multiply this with R, R and R get cancelled, I'm left with E. Isn't that true? So what happens to the potential difference across the resistor? Does it exponentially decrease with time? Yes, it does, and it makes perfect sense, because as soon as I close the switch, the current in this circuit is maximum. If the current is maximum, I times R is going to be maximum. As the current exponentially decreases, I times R or V sub R will decrease, and then eventually it will go to 0 after a very long time. Anybody has any questions about this? All right, then I think the next thing I want to do is, again, I want to take this opportunity to make all of you think about what is the unit of R times C. Okay, what is the unit of R times C? Everybody should take half a minute to talk to a person next to them, and the question is, what is the SI unit of R times C? Please don't waste your time, folks. Everybody should be using this time. This could show up on your exam. Anybody has any thoughts on what should be the unit of R times C? Go ahead, please. Yeah, it is the unit of time, because R times C must have, you don't have to do any work here. All you have to think about the fact that anything that is in the exponential can never have a unit. If you do e to the power something, this something must always be dimensionless. Just like if you take log of something, if you are taking log of something and that thing has unit, you have made a mistake. There has been something wrong. If you are taking exponential of something and that thing has a unit, you have made a mistake. You should step back and think about what you did wrong. Because anything this is just something from the math, high school math that you've learned, which is that things in the exponential can never have any unit. It doesn't make sense. Or something with a log, or something with any kind of log. These things cannot have any dimension. They are unitless things. And that would mean that if the unit here on the top is time, then the unit in the denominator must be time too. So whoever pointed out that the unit of R times C must be the unit of time, so that seconds cancel seconds, so that this thing is dimensionless, is absolutely correct. Does that make sense, folks? Does this thing, do you kind of remember this from high school physics? Something in the exponential, how can it have a unit? That has to be a number, pure number, without any unit. Same with these things. So that's why the unit of this is the unit of time, and I am going to call it tau to denote that it's a very special time. It is called the time constant of an RC circuit. So this time, tau is the time constant of an RC circuit. Now you might say, what is the meaning of time constant? What it means, let's think about what happens when t is equal to tau. So when t is equal to r times c, or t is equal to tau, what happens to q? Look, let's see what happens to q. Do you see q becomes equal to c times e, 1 minus e to the power, instead of t, I'm going to write rc because t is equal to rc, divided by rc, and so this is equal to c e 1 minus 1 over e, 1 minus e to the power minus 1. Do you see this is e to the power minus 1, which is nothing but 1 over e. Do you know how much e is? Does anybody know e is just a number? Yeah, it's like 2.7, right? Close to that. If you put the number of the value of e here, 1 over 2.7, you know, how much will that be? Okay, you can work it out on your calculator. Just do 1 over e and then subtract 1 from it. What you'll find is that this is roughly going to be equal to 0.6, you know, 0.66 times CE. This CE is still there. This thing will be close to, you know, 2/3. Close to 2/3. Similarly, if you try to look at the expression for the current, what happens when t is equal to RC? When t is equal to RC, the current in the circuit, I, becomes equal to E divided by R, e to the power minus RC over RC. This is 1 again. So this is equal to E over R times e to the power minus 1, which is E over R times 1 over E, right, which is close to E over R times 0.33, right. If this is 0.67, this is 0.33. So basically, how are we defining this RC time constant? It's defined as the time when the charge on the plates of the capacitor becomes 0.66 times its maximum value, CE, or you can define it in terms of current and say P is equal to RC, or the RC time constant is the time after which the current in the circuit becomes 0.33 times the maximum current. Does that make sense? Complicated to you? Let's think about the situation in which we just remove the battery from the circuit and keep this thing closed. What do you think will happen in this case? Can anybody say? So we just remove the battery, and now we remove the battery, now we are closing the switch again. The capacitor is now fully charged. What do you think will happen in this situation? Go ahead.
The capacitor acts as the battery.
Good. This time the capacitor will act like a battery. Why will it act like a battery?
It has a potential difference.
Because it has a potential difference. What would these electrons want to do? Because look, there are electrons in this plate, right? And is this a wire? Is this a conductor all the way now? It is. So the thing is, these electrons have now found a path, you know, so that they can go and combine with the positive charges, right? Because there is no battery pushing them in this direction now. So as soon as you close the switch, if the switch was open, then yeah, there is a break here. Because of that, the charges can at the most just go here, the electrons. But the thing is, if suppose the circuit is closed, is everybody appreciating these electrons will start moving in this wire combined with the positive charges. This one will move combined with the positive charges. So basically the capacitor is discharging. Do you see the charge on it is decreasing with time? Is there any current flowing while the capacitor is discharging? Yeah, all this movement of electron is what we call current. This time the electrons are moving this way, right? So what will we say about which way is the conventional current flowing? Opposite. So we'll say now when the capacitor is discharging, a conventional current is flowing in this direction, this way. That's the direction of current, right? Because current is nothing but this flow of electrons, and these electrons are now moving from this plate to this plate. So now The capacitor is acting like a battery. There is no other battery in the circuit. It's the capacitor only, but it's the charges on one of the plates, the electrons on one of the plates that are moving and combining with the positive charges, and this is what current is. So this time you are getting a current because of flow of electrons from the negative to positive. So the current is flowing, we can say that conventional current is flowing from the positive to the negative of the capacitor. And this current we can call the discharge current. How long will it flow? Till the capacitor has gotten fully discharged, right? By the way, I think you should appreciate why it takes forever. Suppose I open the switch, this switch here, you know, why does it take forever for these things to discharge or charge fully? You know, I mean, the thing is, charging or discharging somehow takes a long time because of the fact that these things are exponential. You know, when things get to this flat region, things don't change very much. You know, even here, I may have drawn it so that you don't get the right impression, but the point is, this thing doesn't become zero for a long time. You know, the current doesn't change because of the fact that it's exponential. There is a region where changes are very, very small, you know. So initially it may be a very big change, and then in the exponential tail, things take a long time, right? Exponential tails don't go to zero for a long, long time. And that's why we were seeing here it was not so easy for the thing to go to zero. Like here, I'm trying to discharge it, but it may take a long time to discharge. It may not discharge very easily. Initially it looks like it's doing it very fast, but let's see, you know, how long it takes for the thing to really go to zero. All right, but is everybody clear on this idea that we are talking about? Okay, so if that is the case, let's then try to understand this part, this discharging. What happens to the charge as a function of time when this is the situation? How will our equations change? Can anybody tell me, in this circuit now we don't have any battery, right? If we don't have any battery, how will all this equation change? So I hope everybody is clear about the goals. The goals now are to understand the second part of the curve here, which is the discharging curve, because the charging curve we understand fully. So now, instead of charging the capacitor, we are looking at number 2, discharging a capacitor, because there's no battery here. How will these equations change, folks? Can you look at this thing, this circuit, and tell me what has changed? All I have done is I've taken the battery out, right? If I have taken the battery out, I go from A to B, B to this to this. You know, the only thing that has changed is, what's the only thing that has changed? Anybody has any thoughts on what is the only thing that has changed? Okay, let's redo the whole thing then. It looks like people are not very clear on what has changed, so I want to redo the whole thing. So I hope that you agree with me that we are up to this part we are okay. So VAB plus VBC plus VCD plus VDA is equal to 0. So let's go from A to B. If I'm going from A to B, if the current is flowing this way, I'm going opposite to the direction of current, right? So this time it's going to be I times R, right? If I go from B to C, do you see I'm going from positive to negative? So potential is decreasing. If the potential is decreasing, this is going to be minus V sub C. Going from here to here, nothing, here to here, nothing. So those two things are 0. They add up to 0. So what we have here is V sub C is equal to I times R. Right? Okay, what is V sub C? If you remember, V sub C was nothing but Q over C. This is just true for a capacitor. Q is equal to CV, and that means V sub C is equal to Q over C. Just generally true for capacitor. What is I? I can write I as dq over dt. So this is the differential equation I get. Is this an easy differential equation to solve? Yeah, this is the simplest it'll ever get. If you, as I said, in a differential equation course, the first day you will solve these differential equations, which are ordinary first order differential equations. So what is the answer? What is the solution to that differential equation? It's this. the solution to this differential equation is Q is equal to C okay, Q is equal to Q max, let's say Q max times e to the power minus t divided by RC. And Q max is the maximum charge that you had initially. Okay, this is the initial charge when you started discharging. And do you remember that from the previous thing, what was the maximum charge? Can anybody remind us? It was C times E. Do you remember? So this Q max for us is C times E, and this is e to the power minus t over R times C. What would this plot look like? Anybody? Somebody from the last row, what would be the plot of this Q? This is the discharging, this is the charge on the plates of the capacitor while discharging. So who wants to tell me what should be the charge on the plates of the capacitor as a function of time when you're discharging? Again, you can see it's exponential, right? Let's try t equal to 0. When I use t equal to 0, e to the power minus 0 is 1. So Q is equal to CE. So I start out with maximum charge here, Q max, which is equal to C times E. And then what happens at t going to infinity? E to the power minus infinity is 0. So the charge exponentially goes to 0. And that's exactly what you're seeing in the second part. This thing is showing that initially the capacitor in this circuit is getting charged, and then after it's charged, you're discharging it. So here it's charged and here it's discharging, right? So this was the first part when the battery was there in the circuit. This is the second part where the battery is no longer there, and you have a situation like this where Q as a function of time is exponentially decreasing. By the way, this thing was almost able to discharge. There's still some non-zero value, but the thing is, let's try to do this time constant thing. Remember our time constant was 11 seconds, right? Let's try and see if it works now. So let me reset it. This is the time. Here I'm reading the time, okay? And what I claim is that when this thing shows 11 seconds, that thing will become 0.66. Remember we said it will become 0.66 of the maximum value. So that blue curve, so that's showing how much is the charge. Okay, so let's try. Oh, sorry, I think the problem was that I didn't start this thing on time. Okay, this will still take some time. All right, is everybody clear on this? Any questions about this? If this is Q, I want you to actually work with the person next to you and tell me what should be the V sub C, which should be what? Q divided by C. Shouldn't this be exactly like this? If I ask you what would be the potential difference across the capacitor, do you see potential difference across the capacitor is decreasing with time as it's discharging here? Isn't it decreasing with time? And would it have exactly the same shape because it's just Q divided by a constant C? So this thing also goes like this as a function of time. Agreed? Okay, what about the current in this case? Is current easy to find? Remember, current was nothing but current during discharging. Now we are talking about discharging current. This will again be dq over dt. And what is this? This is d over dt of this, right? Isn't this Q? So it's Q, this is CE e to the power minus t over RC. CE is a constant, so CE just gets pulled out. E to the power derivative of e to the power minus t over RC is minus 1 over RC e to the power minus t over RC. Notice that C and C get cancelled. So basically what we are finding there I discharge then from here turns out to be nothing but minus E over R e to the power minus t divided by RC. What would this plot look like? By the way, what is the meaning of that minus sign? Can anybody explain what this minus sign for the discharge current might mean? It just means that the current this time is opposite to the time when you were charging it. Remember when we were charging this capacitor, we had a battery here and the charging current was flowing this way. Do you remember that? Now the discharging current that we are talking about is flowing this way. As these electrons are combining with the positive charges, we say a conventional current is now flowing this way. So this minus sign just means discharging current is opposite to the charging current, right? What would be a plot of this? I as a function of time. So let's start with some maximum value which is negative, or if you like, yes, maximum value magnitude, but negative means it's the direction is opposite to the direction in the case when we were charging, and this is an exponential decrease, right? Isn't that true? Okay, what about, can we find the voltage across a resistor V of R, which is I times R? Will it be very similar to this? Yeah, because this one will just be minus E over, the maximum value here is going to be minus E here, and then again exponentially it will decrease. Is everybody appreciating that this is the curve for current? And the maximum current is minus E over R. Minus means it's opposite to the direction of current when we were charging. The magnitude of this thing is E over R. So V of R, which is the potential difference across the resistor, should be just I times R, isn't it? Is everybody appreciating that would be the curve for it? Any questions about this, folks? Okay, this time let's try doing this right. Okay, so I'm going to make sure that I press this thing exactly at the right time when, so we want to measure this time when this thing charges. So let me try to turn the switch. Let me do both things at the same time. Ready, go. So I claim that when this is here at 0.66, this thing should be 11. Okay, it shows like 13 or something, but I don't know that I pressed it at the right time. But if I had done everything correctly, R times C should have been this time here in seconds, and that would have been the time when the charge went to 0.66 times its maximum value when I was charging it here. In this case, it'll go to 0.66 times its maximum value, as you're charging it. Here is the maximum value. It will go to 0.66 times the maximum value after a time which we calculated to be 11 seconds. Here I don't know, we didn't do it very precisely. I think we need 2 people. I should have called one of you to hold the stopwatch, the other person to shut the switch, so we made a mistake of a few seconds. Anyway, the idea is RC is the time constant of a circuit, and it tells you when the current will become, say, during charging, when the current goes to 0.33 times the maximum value, or when the charge goes to 0.66 times its maximum value, right? Any questions about this, anybody? Okay, give me just a few more seconds, because the thing is, although we are done with this topic, I want to just give you an overview of where we are headed, because we really actually finished something that was, And we are going to make a transition to something that is going to be somewhat different, because all this time in this course from chapter 21 till now, we have been talking about electricity, either electrostatics, where charges were at rest, or currents, charges in motion. But the point is, in either case, we were talking about electricity. Now we are going to make a transition to magnetism, all right? And everybody has seen bar magnets, right? We all have played with those refrigerator magnets when we were kids, and so all of us know a little bit about magnetism. But here is the thing, one thing that I wanted to tell you is that in this course we are not going to talk so much about the magnetism, that is magnetic fields that are produced by, say for example, bar magnets as much, because the physics of bar magnets is much more complicated, much more difficult to understand than the physics of the magnetic field that is produced by a current carrying wire. It turns out in this course we are mostly going to focus on how do current carrying wires produce magnetic field. The other thing is that even though bar magnets might be good fun to play with, and they might be good fun to put your notes on the fridge and stuff, the thing is they are not very useful when it comes to commercial applications. So in real applications, whenever you're trying to actually think about how to produce a large magnetic field, for example in magnetic resonance imaging, people are literally shoved. If you have an MRI scan done or something, I have had that thing done. Literally I was shoved into this thing where I had a current carrying coil that was producing a huge magnetic field, and they shoved me in and they were trying to look at the scans that were produced, because of this magnetic field. Because it turns out if I have tumor, then it'll be one kind of scan versus if I don't have tumors, etc., etc. But the point is, in all of the real commercial applications, the magnetic fields are going to be produced by current carrying wires, okay? And those are the magnetic fields that we are going to focus on in this course. Once in a while we'll keep referring to bar magnets, but we won't focus on them as much. The other thing about magnetism, just a second, we have 2 more minutes. The other thing about magnetism is that even though in electricity you could get by not necessarily thinking about things in 3 dimensions, in magnetism it is a must. You cannot do anything from day one in magnetism unless you start visualizing everything in 3 dimensions. So suppose we call this X, and suppose we call this Y, and we call this Z. You have to be able to think about all the 3 dimensions, and I'm not going to be able to draw it on the board, but you will. But the thing is, so I'm only going to draw 2 of the things on the board, and I'll say the third thing is out of the board or into the board, and you have to be able to visualize it, because it turns out magnetic forces and magnetic fields and the velocity of the charges, for example, the 3 things are never going to be in the same plane. The magnetic forces are always perpendicular to, say for example, the magnetic field, always perpendicular to the magnetic field and to the velocity of the charged particle, for example, because current is nothing but charged particles moving, right? And that's why it produces a magnetic field. What I'm trying to say is that you have to think about orienting yourself in such a way that you start thinking in 3 dimensions. It's going to be very helpful. So from next time, that's what we are going to talk about. Have a great day.
Professor Singh is a lecturer in the physics department at the University of Pittsburgh. For more information about Professor Singh and her research, visit her website in the description below.